Thank you. Thank you for having me here. Thank you for engaging in a conversation about manufacturing. It's not every day that my subject gets so much attention. I want to talk to you about, this is a new talk for you, the priorities around manufacturing. And that's because what we're seeing happening today is a world, not only your physical world, but the manufacturing world coming closer together. The old paradigm of a buyer working with a supplier over long distances with both physical and manual and interpersonal relationships is shifting slowly, and these worlds are colliding. This collision is happening in the long-term future in very, very significant ways. On the one hand, we will not be sending designs to be manufactured in a machine shop or a manufacturing facility. All we will send is the intent to produce something. We are shifting away from geometries and we're saying we want to produce a motorbike. It should go 200 miles an hour. And then we will have machines on the other side able to tell us what they are capable of producing. And in a manufacturing future that we're talking about today at Singularity University, these two meet in the middle and produce an entirely new manufacturing network that is capable of taking any idea that you have and spitting a product out, right? We are going to have a manufacturing network that is able to determine its own path. It's able to explore the manufacturing sites that need to exist, deal with the fact that certain manufacturing sites may have failure, and give you the part that you need at the moment that you need it. We are going to have a manufacturing network that interacts between machines and humans in ways that are completely seamless. And we're going to have a manufacturing network that ties our machines together without us ever having to interact with that transition. This is the future I want to talk to you about today. A manufacturing network the size of Asia, where hundreds of thousands, maybe millions of manufacturing devices stand at the ready, are reporting their capabilities, and are expecting intent, and are able to process that intent. And so today, what we're going to do is we're going to go on a journey. We're going to go on a journey to understand what is going to make this possible, what are the research priorities that I and Singularity University see in manufacturing today, and we're going to understand why it's so important that we go on that transition together, okay? So, first off, the manufacturing priorities. Think about it at a relatively high level. There are really just three. First of all, we are shifting away completely from an environment where we draw on paper or on a computer the object that we want. What we are learning to do as we speak is to capture intent, to capture what we actually want to do without defining the physical geometry. The second is that we're going to take that information and automatically, without any human interaction, design the final part, called algorithmic design. Jonathan spoke about it as generative design. And then lastly, we're going to be able to match that to the capabilities of a machine. And I want to go through these one by one. I've already mentioned the example of a motorbike, but what this is doing is it's really transitioning us, or the people that work for us, from engineers into constraint managers. Okay? Our ability to define an object, not based on a geometry, but based on our requirements, just pure and simple, our requirements in the most distilled form, is what is required here. There's a company called Entopology in the US that has just started doing this. And what they do is they say, we're not going to design something. We are going to say, at the beginning of our process, we want to build a rocket engine. And this rocket engine should take has this space to operate. Only the the geometric constraints are issued. This rocket engine should be able to exert this much power and use this much resources to do it. And that is the objective that we state for the generative design algorithm. We are capturing the intent pure and simple without actual geometry. This motorbike example is powerful because what it does is it says, hey, let's build a motorbike that can drive 200 miles an hour. And the engine currently goes out and says, this is the perfect engine for you. This is what you should be driving. Anybody want to ride this motorbike? No? You sure? Okay, no, I didn't think so. At the moment, this solution is still being used to inform the designer. It's an old product called Altair Inspire. It inspires the designer to the lines that they must take. But this is so important to the people that are making design software at the moment that they are investing billions of dollars in internally competing projects to make this into a solution that doesn't just inspire designers, that goes on and actually produces the final part design. This is the area of generative design, and it's not only valuable or relevant for mechanical designs, for finished components, it's true too for architecture, right? Autodesk did a very interesting project in Toronto where they said, I want to create buzz, I want to create proximity, I want to have less time that the people spend finding their toilet. And they go ahead and with millions of examples of how the office might be laid out, the computer goes and says, this is the best way your offices should be arranged. And it doesn't only happen at the meta level, this generative design, it's happening at the micro level. What we're doing now is we are using this capability of taking our intent and transitioning it into actual physical designs to design the microstructures of an object. I can't overstate this point. We're designing new materials based on physics, not chemistry. And we're using generative design to do that. Imagine pieces of elastic that if I pull them, they don't contract, they expand, or pieces of metal where I heat them and the side that I'm heating gets cooler, not hotter, because the microstructure of the object is able to move the energy throughout with relative ease. We're able to use this to design new types of products that have better performance than ever before. For example, this material that can lift a kilogram of weight with just 13 grams of mass. Or new shoes that are being produced here in Thailand that are being printed 1 million times over a year with 3D printers. But that's not the amazing thing. The amazing thing is a conversation I had in Brussels recently where the CEO of a football club came to me and said, would it be possible to print a shoe that could correct the player's kick during the kick? I'm like, is that cheating? It is, no? But it's possible, and they're working on it today, right? Because what you need to do is state your intent. We need to know exactly the problem that you want to fix, exactly the kick failure point that you want to fix, and we can use generative design to solve for that specific problem. Our ability to simulate, and that is really what is underlying generative design software, the simulation power that we have amassed, is also able to inform us and tell us how different materials might react against each other. Okay? We now have the power to say, print 2 different materials, they react differently to a given environment, and they will start to self-assemble. This is MIT being humble as usually and making the thing happen with its logo. But the same is true for nearly everything out there that needs to be assembled. We had the conversation with IKEA and talked about how it would be possible to, instead of taking a bookshelf and screwing it together by hand, you could rip off the cover and it would react to oxygen and the bookshelf would grow out of the box. And these things are possible thanks to our ability to simulate and generate designs without a manual assistance. There is no human way that we could go and design this by hand. We need the algorithms to do it for us. And if I talk to you about this, it's because I'm able to rest on 30 years worth of research, an example of which is the DNA assembly. So even at the smallest of levels, we have been simulating and predicting the way things might assemble. In this case, DNA. DNA not only as an information carrier, but a building block. A building block that is able to produce robots that float in your bloodstream, identify cancer cells, and only release the chemotherapy at the point at which the cancer cell has been identified, completely eliminating any kind of inverse reaction to the drug. We have the ability to predict and generate designs and then produce them that float in your bloodstream and identify cancer cells. That is how far this technology has come. And lastly, I want to talk about the ability to express capabilities of machines. And really what this is coming down to is how far we have evolved from a manual machine that reports no data to one that is essentially a computerized factory. And in this ability now, with these sensors and digital information that you all have or may have in your factories, we're able to predict exactly how metal might splatter when we send laser onto metal powder. This is the ability we have in high-grade 3D printers today. And what we're doing is that we're using this information to revolve in a circular way with the machine today. That's our objective, is to create a closed-loop system that speaks with the machine and corrects the machine's actions when it detects that these splatter occur. That's great. I think we've done a great job getting to where we are. But essentially what's happening is that we are making machines act like ivory towers. These are highly computerized machines, and yet we are not connecting them. It is estimated that less than 5% of manufacturing data today is being utilized, right? And that's despite the fact that we need it. When I say we need to find a way to identify the machine capabilities, we need more than just to identify the splatter into a machine. We need to identify exactly what it is capable of producing at every second. Whether we measure the tolerance of the machine. It has worked for 6 months or 3 months without any maintenance, and therefore it's only possible to manufacture at this type of tolerance. Right? That's the kind of information we need to have, and we need to report back into the manufacturing network I've just spoken about. The reason we need this so urgently is because there is almost no way for us to keep up with the constant evolution of manufacturing capabilities. When I started giving 3D printing talks and digital manufacturing talks, around 2014, I kept on getting questions about our ability to print because it is so slow, right? Everybody had this question for me. And then in 2015, HP came out and said, I've got a printer for you that is 10 times faster than anything you've ever seen before. And I said, that's great, I'm very happy. And then just 3 months after that, Carbon, which is a company that was funded with $500 million in the San Francisco area, came out and said, I'm able to produce something 100 times faster than anybody has printed anything before. So within 3 months, all the questions that I ever got about speed disappeared. But how are we supposed to keep on understanding which machine is suitable for which kind of part if the evolution of the machines is so fast? And it hasn't stopped there. Now, Lawrence Livermore Lab just a few months ago announced a machine that is capable of producing an object with just a flash of light. The evolution isn't stopping. Our ability to have the machine report exactly what it is capable of producing at every second of every day is a crucial element of a manufacturing network as I described it today. And one thing that gives me hope in that transition is the journey we have been through with 3D printing. Now, I won't speak about 3D printing applications because you have a lot of experts coming up in the next 2 days capable of doing that. But I do want to speak about the history of evolution in 3D printing because, as Jonathan said, it's a relatively old technology. And when patents started expiring in 2007, the prices dropped tremendously. This was the cheapest printer available at the time. 2007, $18,600. Who wants to guess the cheapest printer that came onto the market after the patents expired? $5,000? $1,000? $699? Here, a business guy in the front row. I love it. I'm not buying anything, sir. $400 came out that. So the prices dropped incredibly thanks to the expiration of patents. And all the incumbents in the industry obviously thought, oh my goodness, my business is destroyed. What am I going to do? So they came out and said, okay, we're going to innovate in other areas. We're going to innovate in materials. And we came out with thousands of different materials that we can now 3D print. Titanium, silver, ceramics, gold, all kinds of different polymers are now available to us. And we came out with evolution and form factor too. You're going to hear about 3D printing food and 3D printing in space, but we're now also 3D printing at incredibly large scale and incredibly fine detail. We're printing pharmaceuticals for you that have the amazing ability to be digested at the exact rate that we want it to be digested to impact your immune system. And that transition from expiration of patents through the incumbent reaction and the startups generating these new form factors and new materials is exactly what is happening in every other manufacturing industry that is going digital. Because as you heard today, as soon as a domain enters a digital era, we are able to equate it roughly to Moore's law. So if it is collaborative robots, if it is digital knitting devices, if it is new types of carbon fiber assembly structures, or CNC machines, or bricklaying equipment, all of these have one thing in common, which is that they have become software-driven manufacturing devices. And in doing so, they have entered the same kind of evolutionary curve that we have seen in 3D printing. So if you are in an industry that is using a manual machine and is transitioning to digital, don't expect the evolution of that machine to be at the same rate as the evolution of the manual machine beforehand. Expect it to be a lot faster. So these are the three research priorities that we're seeing. The generative design paired with the ability to capture intent and the ability to capture exactly what the machine is doing and coming together in a manufacturing network. That is what we're seeing. But none of that is going to work without a fourth vital ingredient, and that is the interaction between people and machines. We have come so far in that interaction, but in the wrong direction. Because what we have focused on in the last 30 years has been exclusively to make our manufacturing much more productive. We have focused on lights-out manufacturing. Every attempt was made to eliminate the human from the factory. That does not make the manufacturing network more agile. It makes it much, much more expensive. Right? Transitioning this type of factory from one car to a different car type costs $200 million. Just ask Ford if they wanted to, when they wanted to change the manufacturing, the material that they used for their Ford 150 truck, it cost them $150 million per factory. Okay, so this technology evolution hasn't brought us in the right direction. What you're going to hear about today is a different direction. You're going to hear about the ability to have AR and VR, exoskeletons, and other technologies that augment the human, as Jody just mentioned. But I think what we're seeing beyond augmentation is even more exciting. What we're saying is an entirely new paradigm of enabling technologies. So these enabling technologies don't wait for the IT team or the manufacturing team or the industrials team within a factory to come and replace a task with a human. What they do straight away is they give the power to make those amendments to the people that know the tasks the best. Jody spoke about 3 out of 5 jobs being eliminated with automation. These aren't actual jobs that are being automated. These come in automating individual tasks. An individual worker within a factory may do thousands of different tasks, micro tasks that are available to them at any point in time. And McKinsey's study actually says those tasks are the ones that are going to be eliminated. So a human might be left with 30% of his tasks, 70% have been automated, but those 70% need to be identified, need to be automated. And this enabling technology, whether it's a collaborative robot that can be assembled by the person working on the factory line, or whether it's a jig and fixture that they can go into an online environment and just create themselves instead of waiting for somebody to come and do it for them, or a machine learning algorithm that you can just drag and drop into place the same way you might drag and drop a website into place. These are the tools that enable people. These are the tools that you can give to anybody working in your environment, and they can take those tools and start addressing the problems that they have, the problems that they know about, the problems that they want to eliminate. What we were able to do as a result of this is maybe among the more exciting technologies. So what you're seeing here is really the biggest example of our ability to, biggest example of enabling technologies. A phone that has more sensors in it than a whole Xbox had 5 years ago. Right? Able to identify your face, but also able to scan your whole environment. We're shipping way more of these tools than ever before. Right? These are the tools that are able to allow somebody who never designed anything in the past to go and scan their environment and create their own designs. So if they're in a factory and they see a production line and they see that there's a part missing or they want to make a suggestion in 3D, they can just scan their environment with their phone and make that amendment on their phone, their suggestion on their phone. That's an enabling technology, as I mentioned. And the reason I know that these enabling technologies are being deployed is because the manufacturing networks that I mentioned to you earlier on are already starting to happen. We have seen an evolution of manufacturing networks especially in America over the last 10 years. Many of you might have heard of Proto Labs. Proto Labs, one of the best publicly traded examples of short cycle manufacturing in America today. But what they are being challenged by is the next generation of manufacturing networks. For example, Xometry. Xometry just announced 2 days ago that they raised $50 million, and Xometry has nearly no assets, no factory. What they have instead is a manufacturing network of suppliers that are offering their spare capacity on their network, Uber for manufacturing. We call it manufacturing as a service in the States. But what that is being challenged with today is a request that my company is getting from many different buyers, for example, Honeywell or BMW. And they're saying, we know our suppliers, we know who we would like to work with, but we want to know exactly what is happening on their manufacturing devices at every minute of every day. So they are asking us not to create a new Uber for manufacturing. They're saying, how can I get insight into the specific action of the specific machine in the spare capacity, in the quality of the production? And so that is something that we're working on, and which is why I know that these manufacturing networks are already starting to happen. The research priorities that I mentioned to you today are being addressed bit by bit, and we can see it in these networks that are evolving. And I think the three core reasons why we're seeing this are the drive towards an improved supply chain, the core requirements of increased agility, and finally a pressure to develop more business models than we've ever seen, more exciting business models that are able to drive your profitability and your exposure. So let's talk about supply chain failure first, because it is the element. Sorry, it is the element that brought me to this topic 10 years ago. A plane crash in Nigeria that killed 159 people because a part was broken, and the company that made that part couldn't deliver it for 3 days. Right? So we had an instance of supply chain failure that actually cost a lot of lives. And this is not just something that happens in Nigeria. This is something that is happening all across the world. Every factory here has a problem with supply chain failure, right? And so this driver, this ability to meet that point of failure, is something that I think that a new manufacturing network is the reason why a new manufacturing network is absolutely required. The second is much more tangible to those of you in this room today. The second is agility. Jody already mentioned this. Agility is driving us in 3 dimensions. The first is the fickle consumer, who at any point in time can get a digital product at the tip of a finger. They can transition immediately from an idea to a book, a movie, news, music, whatever they want, they can get it. But a physical product? I was just speaking to a family running a confectionery business, and just to bring out a new type of sweet will take them 2 or 3 months, right? 83% of Kickstarter projects are delayed, right? That have a physical component in them are delayed, 83%. So the way that your factories today react to that problem is to produce a much broader variety of parts so that whatever the customer needs at any point in time, it is available for them immediately. The problem is that this strategy fails because the manufacturing devices, because the working capital requirements and the profitability goes down. It's not an ability to be agile and react. It's an ability just to drive your warehouse inventory. Lego noticed this in the early 2000s, and when they doubled their products that they were producing, their profitability went down, they started making a loss, and the moment they cut their parts back from 12,000 to 6,000 again, they started making a profit again. So we see this in factories that use traditional methodologies to react to this increased demand for agility among customers. They fail. And this is just going to get worse. If you think about jet engines that fly across the Atlantic, they generate 5 terabytes of information every time they fly. We could use that information to generate better better plane engines for the Pacific crossing, the Atlantic crossing, the Saharan crossing. But we can't because it takes 10 years to transition an idea into a jet engine. The same in real estate. Despite the fact that we now have more information available to us about the urban landscapes than ever before, thanks to autonomous driving, we can't just take that information and generate better buildings or shopping experiences or lifestyle choices for consumers, because it takes a decade to turn an idea into a real manufacturing experience, lifestyle. And the third is DNA. It'll soon be cheaper to get a full-body DNA scan than to flush the toilet. We could use that information to design better, more personalized products for your body. But we can't because it takes years to get those products into the market. The second example is on energy, or on markets. right? The driver here is the fact that the market reacts with increased speed to any change in the environment. Now, if you were a company in 2014 and did not use oil as one of your raw material inputs, you would have lost out on the decline of the oil price in 2014. 43% decline on just 0.7% change in demand. Humongous difference. If you could switch from whatever raw material you were using to the raw material that had a price decline like that, you would immediately make 43% more profit. But you can't, because the manufacturing lines are lined up for the specific raw material input. If you are a company that uses energy, and nearly every company here does, but especially in heavy industries, energy is a very important constituent of your pricing. Now, in Europe, prices declined below 0 for energy at 3 points last year. If you could use that price decline to make all the inventory that you needed in that time period, you could save up to 50% of your total expenditure. And if you tell me that your industry is not capable of such rapid reaction, then I give you the example of modern meadow. And we'll speak about biocultured meat and leather, but the ability to take an asset-intensive industry like meat and leather that is currently eroding all of the Amazon, and transition that into a warehouse, a 5,000 or 10,000 square foot warehouse in Wisconsin that is able to produce on demand whatever meat or leather you want. You can't tell me that if an asset-intensive industry like meat and leather is able to make that transition, that your industry is not able to make that transition. The third driver for agility is politics. Now, I am the product of a European exchange program, so this hurts me. But I think it hurts everybody, except maybe for Thailand. You're kind of benefiting from the skirmish that we're having with China and America right now. But what we're seeing at the minute is that every company is having to start to think, okay, I cannot use supply chain as a proxy for agility anymore. It used to be that I could make trains in one place. And if Brazil did not want any more trains, I could just ship those trains to Europe instead. That is no longer possible, right? We need to make the trains in every political environment to be able to react to closed borders, to increased taxation. We don't have the luxury of using supply chain as agility anymore, as a proxy for agility anymore. So that is summing up. Those are the three drivers towards agility that I'm seeing and that are encouraging the increased adoption or the increased spread of the technologies that will allow us to build entirely new manufacturing networks. But the most exciting is perhaps also the most tangible. Because what we're seeing happening at the moment is cars. Cars that are being built and designed in entirely new ways. Cars that drive around with sensors laden all around them. And as they drive around their environment, they're capturing data about how that car might react, or how the pollution or the road or the driver's style might impact the car. And that information is being poured immediately into the design of a new car, so that we're seeing a consistent evolution of the machine just based on the sensors that are a part of this environment. We recently spoke to the the Department of Defense in the US, and they're starting to think about drones that are flying across battlefields. And as they're flying, they're capturing feedback about the reaction that they have to this battlefield. And immediately a new drone is designed to address that failure point that the previous drone had, and is being printed on a plane as it flies across the battlefield. Or a CT scanner that as we are scanning, we are designing the custom implant for you. And you are being rolled off the scanner right into the operating theater, and your custom implant can start being produced. Instead of having to wait 4, 6, 8 weeks for that custom implant to be ready. Or a plane that as it's landing, a sensor discovers that something's breaking. A machine learning algorithm identifies why it's breaking. And we send this information directly into a generative design algorithm that redesigns the part to address the point of failure. And before the plane has even landed, a part that is better than the part that has not yet failed is already being produced. That is a business model that I encourage everybody here to start thinking about. One in which we start thinking about product evolution in terms of seconds instead of years. That is how we meet both the need for customers, but also the need of industry. And it affects every company here. So if you have a question on why this is impactful for you, or how you can transition this into something that benefits you, I really encourage a conversation. I've met some of you today already, and I will be here for the remainder, and we can have those conversations, and we can go on that journey together. Because as you've seen today, the technologies are here. The technologies are, the priorities for further evolution of the technology are clear. And the reasons for doing this are also clear. There is nothing standing in our way of creating new manufacturing networks in the future, and I can see the start of them already emerging. Thank you very much for your time, everybody.